Hello, today we're going to demonstrate what you know about moments already using a simple demonstration with a ruler, a matchbox, a couple of 20-cent pieces and a couple of 5-cent pieces. If you could please get these for yourself, stop the video and come back with them. Okay, so we're going to use the ruler as a beam for a seesaw and a matchbox as a fulcrum. Assuming our beam is a uniform weight, and so its mass, so its force acts down in its centre, we can see that the fulcrum can hold it up at the centre point. Now, usually when you have a seesaw, as you probably know from experience, we're going to say we have two people here, person 1 and person 2, and person 1 might get on the seesaw over here, and when they do, the seesaw tips down. And what children don't know, but what we know, is that that's because this person here has a line of force acting straight down through here. And that line of force has a perpendicular line back to the pivot point. And together those two things create a moment, a twisting action in this direction, which is the clockwise direction, and we call it the negative direction. So usually then what happens, because of that twisting motion, another person then goes and gets on the other side of the seesaw and they shuffle around a bit until they get themselves balanced. They try and balance. And when they balance, we can see that's because the clockwise negative moment twisting that way is equal to the counterclockwise moment in the other direction. Well, here we have the system drawn here. Here's the beam, and we're saying this beam is going to be 6 units long, and there's the fulcrum there. And for our purposes, let's make this 20-cent piece have a 2 Newton force. And let's say a 5-cent piece, which will appear later, has a 0.5 Newton force. So here, okay, I'll stop the video and see if you can write the equation for the two moments, one on each side, one created by this person, one created by that person. Write the equation that describes this system in equilibrium. Okay, well, here's our system here. There's our beam, and we have at one point here, at distance 5, we have the 2 Newton force acting down. And the 2 Newton force has a line of action, which is a straight line going through the beam, and the moment arm for that is the perpendicular distance from that line of action back to the fulcrum, which in this example is exactly along the beam back to the fulcrum. So the moment here, which we always know it's force times the perpendicular distance, so here in this case it's 2 newtons down times 5 will make it meters. Okay, so that's 10 Newton meters. And similarly on the other side, we have a moment acting due to a 2 Newton force acting down. Its line of force is going straight through the beam, and it has a perpendicular arm back to the fulcrum, and so this moment here is also the 2 Newton force down times the length of its perpendicular arm, which is 10 Newton meters. And we can write this system in equilibrium. In equilibrium we know that the sum of the moments is equal to 0, And we can see clearly from this that this moment in this direction, this one down here, we know it's counterclockwise, so it's positive, and this one over here is clockwise, so it's negative. So the sum of the moments is plus 10 Newton meters from this direction and minus 10 Newton meters from that direction, which is equal to 0. Now, let's say that this person here, which does happen in real life, one person decides to move in. This person's going to move into 4 away. Now, what's going to happen to the seesaw? I'll stop the video and see if you can describe it in terms of moments. Okay, so what happens, of course, is that person's end tips up because they have decreased their distance. And so now their moment, which is going down in the clockwise direction, is actually overwhelmed by the moment of the person on the other side whose moment is going in the counterclockwise direction. So clockwise is overwhelmed by counterclockwise and the seesaw tips up. Now usually what happens then is someone else gets on and sits pretty close to the person who's moved in, which once again balances the moments. And the reason that works is because total force due to their total weight times their distance now balances the force times distance on the other side. Now, I'll stop the video and see if you can now draw the equations for this system. So, if you set up your ruler and your matchbox system to look like this one and then write down the equation, what do you get? Okay, so now we have at distance 4, we have the 2 Newton force, and we also have the 0.5 Newton force, both at distance 4. And still back at distance 5, we have the 2 Newton force. So what do we have together? Well, once again, both of these have a line of action going straight through, and the perpendicular arm back to the fulcrum is now of length 4. So the moment over here, which is force times perpendicular distance, well, the force now is 0.5 plus 2 newtons times the distance, which is 4. So that's 2.5 times 4, which is once again still 10 Newton meters. And because it's round in this direction, it's going around in that direction, the clockwise direction, we know it's negative. Okay? Over here, we still have the original moment we did before. We have 2 newtons times 5, which is equal to 10 Newton meters. And because it's going around in that direction, the counterclockwise direction, we know it's positive. So once again, the total equation is the sum of the moments is equal to 0, is equal to plus 10 Newton meters from that one, minus 10 Newton meters from that one. So you can see that to create the moments in either direction, you need to work out what the total force times distance is on each side, and in statics we have equilibrium systems where they balance each other out. And that is how you can describe moments in a simple system.